I am here to present the video lecture on subject signal system BEC 403, and this is my second lecture, and the topic of the lecture is continuous and discrete convolution. I am Dr. Amit Garg, Associate Professor in EC Department of Akgec. So let us start with the introduction of continuous and discrete convolution. So now you can see continuous convolution is also called convolutional integral, and discrete convolution is also called convolutional sum. So if either of these given, then it means that you have to solve this continuous convolution and discrete convolution. Another name is convolution integral and convolution sum. Now you can see here the convolution integral is defined like yt equals to xt convolution ht, and the expression is yt equals to minus infinity to infinity x tau into h t minus tau d tau. So let us see how we are getting this. This is like we are having an LTI system, continuous time LTI system, let us suppose, and for continuous time LTI system, let us suppose the impulse response is ht. We are applying input xt to this system so that we are getting the output yt. Okay, so if we have to calculate yt, we have given xt and ht, then the output of this LTI system is the output yt, which can be obtained like using this expression where tau is a dummy variable. Okay, and similarly if you will see the convolution sum, in case of convolution sum we are having an discrete time LTI system where impulse response is hn. We are applying an input xn to this system to get the output yn. So whenever we have to find out the output of any LTI system, basically we will perform the convolution operation. Now depending upon our signal, if our signal is continuous, then we will apply this continuous time convolution, which is also called convolution integral, and in case of discrete it is called as convolution sum. Now you can see this convolution sum expression is yn is xn convolution hn, which can be written like yn equals to summation k equals to minus infinity to infinity xk into h of n minus k. Here in this case k is dummy variable. Okay, so this is how we can calculate the output of any LTI system, whether it is continuous or discrete. Okay, now we will see another important thing is that here we have taken that one signal is the impulse response of the system, but it is also possible that convolution can also be applied for two signals, two arbitrary signals x1t and x2t. Okay, you can also find out the convolution between these two sequences or signals, and here again for between x1n and x2n. Okay, so now let's see one problem. Find the convolution of x1t equals to x2t equals to t times ut. Okay, so this problem is not a typical one. This is the simple problem, so I don't think so that there is any requirement of plotting the graphs. And you can see here both the signals are having ut, so it means both the signals are causal signals. Okay, so when both the signals are causal signals, then finding convolution is quite simple. Okay, so now we will use the expression x1t convolution x2t, that will become x1 tau into x2t minus tau d tau. Okay, now we will write, now first of all we will calculate x1 tau. So x1 tau can be calculated by putting tau in place of t. Okay, now we have to calculate x2t minus tau. So x2t minus tau can simply be calculated by putting t minus tau in place of t. So we are having t minus tau u t minus tau. Okay, now we will put these values here, t tau u tau and t minus tau u t minus tau d tau. Now we will see we are having u tau and u t minus tau. Okay, so now let's see what is the meaning of u tau. U tau is some signal which is somewhat like this. Here it is tau, this is u tau. And whenever we are talking about u of t minus tau, so u of t minus tau is some signal, u of t minus tau is somewhat situation like this. So this value is t. So this is u of t minus tau and this is tau. Okay, now you can see this u of t minus tau will only overlap with this u tau when this t is greater than 0. If t is less than 0, then in that case situation will be somewhat like this, situation will be somewhat like this. So there is no overlap, so it means you will not get any output. You will get only output when t is greater than 0. So when you will overlap it, so you are having somewhat this type of region. Let us suppose I am superimposing it with another one, so we are having, this is the superimposition. Okay, so limit is 0 to t. So that's why next step we have written 0 to t, and another things will remain same, means tau, t minus tau, d tau. Now you have to simply find out the integral tau and t minus tau d tau, where limit is from 0 to t. So important thing is here is that how we will finding out the limit. Okay, so if you will be able to finding out the limit, then it is very simple to find out the final output, or our system output, or the convolution of two signals. Okay, now we will simply integrate it. So when you will integrate it, t is constant and tau integration is tau square by 2 and limit is from 0 to t, and for another one it is minus tau square. So tau square is tau cube by 3 and you will put limit 0 to t, and when you will solve it, you are finding that the output is t cube by 6 into ut. Why ut is there? Ut is there because this signal or this output is only defined for t greater than 0. We have seen that we are getting the output only when t is greater than 0. That's why we have to put it here, u of t. Okay, so this is the simple problem. We have seen this problem when both the signals are causal signals. Another problem that is somewhat different problem based on continuous time signals also. So we are having a rectangle signal which we can also call as gate function. So we have to find out the convolution of a rectangle signal with itself. And rectangle signal is defined for minus t to t, and where the value of magnitude is a. So you can write this question in various manners, like a rect t by 2t, where 2t is the width of the rectangular signal. This is the total width from minus t to t, so that is equal to 2t. So you can write a rect t by 2t or a pi t by 2t, or a or 0, and this a is defined only between minus t and capital T and capital T, and the limit is, and the amplitude is a. Okay, and you can also write this equation like find out the convolution integral for a system with input xt and impulse response ht. So xt equals to ht equals to this, and this signal can also be written in form of gate function. So a times ut plus t minus ut minus t. So there are various manners by which this question may be asked. Okay, so let us see how we will solve this. So you know the definition of convolution. According to definition of convolution, output yt can be obtained by xt convolution ht. Okay, where ht is the impulse response. Okay, so the formula is x tau into ht minus tau d tau. Okay, so first of all we will see like, first of all we will draw the various waveforms like x tau. This is your signal xt. First of all we will draw the signal xt and ht. So this is signal xt, and similarly the signal ht is the same, again defined from minus t to capital T, and the amplitude is a. Okay, so now x tau simply we will obtain, in place of t we will write tau. So we are having this waveform for x tau, and from here we have to find out, according to this expression we have to find out the value of ht minus tau d tau. So how we will obtain ht minus tau? So first of all we will draw h of tau. So h of tau is nothing but the same signal, it is lying minus t to t, 0, a, and h of tau. If you will draw h of minus tau, so what happened? This minus t will come over here, this t come here, magnitude is same, so there will be no change. So that's why h of minus tau will remain the same. H of minus tau will remain the same. So I am writing here, in place of h of tau, now I am writing h of minus tau. Okay. Now we have to find out h of t minus tau. T means we are shifting our rectangular signal by an amount t to the right direction. Why right direction? Because already minus t is there. This signal is already reflected. So plus t means we are shifting this signal to right. Okay. So if we are shifting this signal to right, then what happened? Depending upon the value of t, which is the shifting parameter, this t, if t is, what happened if t, if we are shifting it by t, so what happened? This value will become t minus t and this value will become t plus t. Okay. We are adding t, small t on both sides. Okay. Now depending upon this value of t, you can see if this value of t is less than 0, it means this is negative quantity. So rather than shifting right, the signal will shift left. Okay. And similarly here in the case. So we don't know about t, that whether this t is positive or whether this t is negative. We will explore all the conditions, that whether t is greater than 0, less than 0, and check the overlapping of this signal. So this figure that I have drawn here is nothing but an arbitrary type of signal. We don't know about right this time key what is the value of t. Okay. Now we will see the various cases. Like first case, we will check. Here you can see this value is t plus t, and this signal is our first signal and this is now second signal. Okay. Now we will perform overlapping. Okay. So when we will shift it by t, so now this will become h of t minus tau. Okay. Now we will see this t plus tau, one signal is this and one signal is this. Now we are superimposing this signal to this signal by taking different values of small t. So first case we will consider that this t plus t will be less than this minus t. T plus t will be less than minus t. So in this case what happened? This t plus t will be on the left side of this point minus t. Okay. So what happened? In this case, signal do not overlap. You can see this is the situation because this t plus t is less than minus t. So because there is no overlap, so the product of the integrand is 0. So the value of yt will become x tau into ht minus tau, d tau will become 0 for this condition of t. Okay. Next condition we will prefer that this t plus t point will be lying somewhere here, means between minus t and t. So you can say this t plus t point will lie between minus t and capital T, minus capital T and capital T. Okay. So the situation is somewhat like this. Now this t plus t point will come here and minus t is here, and this is the only overlapping area which you can see over here. Okay. So when we have to find out the area which is the convolution for this limit, so we will perform this limit from minus t to capital T plus t, and in this case what is the value of magnitude of signal? For this signal it is a and for this signal it is a, so it will become a square and d tau. Okay. So this is your a square d tau, limit is from minus t to t plus t. So it is simply you will solve it. So you will find a square times t plus 2t, a square times t plus 2t. So this is the value of output when this t plus t point is lying between minus t and capital T. Okay. And this is the value of t, where t is lying. Third case is somewhat like this, that this signal, this t plus t is lying between minus t and capital T, and the next condition is that this t plus t will pass this value t, and this t minus t, in this case when it will happen, then t minus t will be lying between minus t and t. So third condition, you can see this t minus t point is lying between minus t and capital T. Okay. So in this case situation will be like this. Here is your point t minus t, and here is your point, this is your point t, and this is your point t minus t. Okay. And this t t minus t point is lying between minus t and capital T. Okay. So, in this case we can see the overlapping area is this. So, the limit is from t minus t to capital T. Again the amplitude is a into a, that will become a square. So, you can easily solve it to get a square times 2t minus t. Okay, this is the simple integration. If you will solve it, then value is integration t minus t a square d tau, because a is constant. So, we will take it outside. So, a square integration t minus t to t d tau. So, the integration of d tau will become tau. So, a square tau limit is from t minus t to t, and when you will solve it, then you will find that it is a square 2t minus t. So, when you will put the limit, so it will become a square times 2t minus t. So, this is how we can calculate the output for this region. Now, again the situation is like, now this t minus t point will lie right to this point t. So, what happened? Again there will be no overlap in these two signals. So, when there is no overlap in these signals, again then the output will become 0. So, this output, when this situation arises, then t is greater than 2t and the output is 0. So, now if you will see as a summary, then you have seen that the first output is 0, then for second case output is a square times 2t t plus 2t, and in third case output is a square times 2t minus t, and again in fourth case the output is 0. So, this is the condition that we can write it. Okay. And as a combination, you can write this output in form of delta function, in form of triangular wave, triangular signal, okay, where the width of the triangular signal is 2t. Okay. Although you can write this expression like in this manner only, still if you want, then you can write it like this also. So, this is the basically the output. Again you can combine in more compact form. So, you can write it like a square times 2t minus mod of tau, where mod of tau is less than 2t. Okay. So, this is the output signal. If we want to draw the output signal, then we can also draw, and here in this case we can see that the output is basically the triangular signal. Okay. So, this is how we have calculated the output in case of, you can see here, both these signals, rectangular wave signals, are basically rectangular signals are non-causal signals. So, here is the output in case of non-causal signals. Okay. Now, one problem we can see from discrete convolution. Okay. So, let us suppose we are having sequence xn, which is given as 0.8 to the power n un, and hn, that will be equal to 0.4 to the power n un, and we have to find out the convolution between xn and hn. Again, you know, the output yn will become xn convolution hn. The formula is yn equals to summation k equals to minus infinity to infinity xk into h of n minus k. Now, we will simply put like xk we will obtain by putting n equals to k in this above expression. So, we are having 0.8 to the power k uk, and h of n minus k we will simply obtain by putting n minus k in place of n. So, this will become okay. Now, again we will see what is the overlap, okay. So, case 1, when n minus k is less than 0, there will be no overlap. You can draw these signals also, or I am just taking these signals for understanding purpose. Otherwise, these values are less than 1. So, you are getting the graph accordingly. So, uk is somewhat, this is your k and this is uk, and u of minus k if you will draw, then u of minus k will become this is u of minus k. Okay. Now, if you have to draw u of n minus k, then again this graph will be shifted by k unit. Okay. Now, depending upon this k value, your overlapping will be there. So, we will check the various values, what is the value of n minus k. So, if condition is that if n minus k is less than 0, it means, let us suppose we have drawn and we have checked that this is u of n minus k and this point is somewhere here, and this our signal, another signal is here. So how we will get the overlap? So this is the condition when n minus k value, because when you will shift it, this point will become simply n minus k. Okay. So we will check this n minus k point, whether this n minus k point is less than 0 or greater than 0. So pehli condition, first condition is that u of n minus k is less than 0. So when n minus k is less than 0, then there will be no overlap and the output is 0. Another condition is that n minus k is greater than 0. So n minus k is greater than 0 means your situation is somewhat like this. So this is basically our overlapping area. Okay, so we will find out the convolution here. So for this we have taken the equation again. Now in this case, what happened? This point will become somewhere here and limit is from 0 to n. Okay, because u of minus k, and when you will shift it, then it will shifted by minus k and this point will become now n. So this point will become n. Okay, so 0 to n, here we will put the limit 0 to n, and here 0.8 to the power k, 0.4 to the power n minus k. Okay. Now because n is constant, you can take it outside. So again 0.8 to the power k into 0.4 to the power minus k, which we are writing as 2 to the power k. How? 0.8 to the power k, and 0.4 to the power minus k is 0.4 to the power k. So simply you can write it like, after dividing you can write it like 2 to the power k. Okay, after so we are getting this 2 to the power k, and the final result, if you will sum this 2 to the power a k, which is a GP series, and sum of n terms series, but here we are starting it from 0, so total terms are n plus 1. Okay, so what happened? The solution of only this part is 1 plus 2 plus 4 plus like this. So what happened? First term is 1, r to the power n. So common ratio is 2. N is total number of terms are n plus 1 minus 1 upon r minus 1. So that's why this will become 2 to the power n plus 1 minus 1. And why un? Un we have taken because this is the condition where n minus k is greater than 0. So in this condition, you can see this will become the output un. Okay. Again, you can check also this because both of these signals are causal signals. So your result will become causal also. Okay, that's why we have put un at the last. Okay. Now we will see relationship between LTI system properties and the impulse response. Look, the impulse response is itself a very important aspect. If you will know the impulse response, then various properties of LTI systems can be judged by simply knowing the impulse response. Okay, or you can say LTI system response or impulse response of any LTI systems are completely determined by its impulse response, or you can say LTI system or the characteristics of an LTI systems are completely determined by its impulse response. Okay. So various properties we can find out with the help of impulse response if we know this. Then first property is LTI system with and without memory. So here we will see what are the conditions. If those conditions met, then our system will become with or without memory system. So you know, with memory systems are dynamic systems, means systems having memory, and without memory systems are systems without memory, means memoryless systems. Okay. So if you will see, so if in case of memoryless systems, the present output of a memoryless LTI system depends only on the present input. Okay. Because there is no memory, so if we are giving the input, we are getting the output. Simple. Okay. So now you know the definition of convolution, Hn convolution Xn, because this is commutative. So rather than writing Xn convolution Hn, we are writing Hn convolution Xn, which we can write like Hk into x of n minus k summation k equals to minus infinity to infinity. And if we will basically expand it, so we are having this type of term. Okay. For the system to be memoryless, Yn must depend only on Xn, means present input, and therefore cannot depend upon Xn minus k, where the value of k may be minus or plus both, other than 0, because for 0 your input is get multiplied from here. So hence every term in the equation must be 0 except h0 into xn. This condition implies that hk equals to 0 for k not equal to 0. Okay. So thus a discrete time LTI system is memoryless if and if only if hn equals to k times delta n. Okay, because we have to obtain this condition only. Okay. So because this is defined only at n equals to 0, so delta n we have put it. Okay. So and delta n is only defined at n equals to 0, so we are getting this term, and k is some constant. Okay, where k equals to h0 is a constant and the convolution sum reduces to the convolution yn equals to k times xn. Okay. So if a discrete time LTI system has an impulse response hn that is not identically 0 for n less than 0, then the system has some memory. In case of continuous time LTI systems, you are getting the same type of situation and same type of condition, that is yt equals to k times xt, where impulse response is ht equals to k times delta t, like here we have obtained hn equals to k times delta n. Okay. Now second condition is causality for LTI systems. So output of a causal system depends on the present and past values of the input to the system. It is not dependent upon the future values of the input. So that's why we have written this convolution definition like this, and we have splitted this convolution from minus infinity to minus 1 and this expression, and then from 0 to infinity, and then we have basically open this summation signs, and we are getting this equation. Okay. Now we can see here the past and present values of the input, which is x and xn minus 1, are only associated with indices of k, like this hk, where k is greater than 0. So in the impulse response hk, while future values of the input, these are the future values which are defined for values of k which are less than 0. So if we want that our output should be dependent upon present and past values of input, then this h of k values for indices less than 0 should be equal to 0. So you can see the condition is hk equals to 0 for k less than 0. Okay. And similarly for discrete convolution, similarly for continuous time causal system, you can find out the condition is ht equals to 0 for t less than 0. And also when this condition met, and we are only interested in causality of LTI systems, then this part will become 0. So our equation will reduces, or convolution equation will reduces like this. So this you can see here. Okay. Now we will see the stability of LTI system. So system is stable if every bounded input produces a bounded output. You know, you are giving, if you are giving a bounded input or a small input, if we are getting a small output, then we can say this system is bounded. So the conditions on Hn that guaranteed stability of system by bounding the convolution sum are presented here. The magnitude of output is given by like mod of yn. We are having equation yn equals to Hn convolution xn. We have taken mod on both sides. Then we have written the condition of, we have written the expression for convolution. Now as per theorem that the absolute value of summation is always less than summation of absolute values. So we are writing it like this, and then again we have expanded it, multiply, we are having mod of hk into x of n minus k, we are having this hk into x of n minus k, which we can separate it in mod like this. Now if input is bounded, then we can write that this input is less than bx, this is less than infinity, where bx is some finite quantity. Okay. So what happened, if this is finite quantity, then even if delayed it, then again it will become finite. So if it is finite, then output yn can written like this, bx summation k equals to minus infinity to infinity mod of hk. Now we know if this yn should be less than infinity, from the above equation it can, if impulse response is absolutely summable, absolutely, here the stability is dependent upon this impulse response. So if it is absolutely summable, means the value of this term is less than infinity already, and if this term will become less than infinity, then the whole system will become stable. So that's why the condition is this term should be less than infinity, and this is the condition for the impulse response to be absolutely summable. And similarly, if you will see, this is the expression for continuous convolution. Again we are getting this condition, similar condition, again this quantity is finite quantity. So what happened, for an continuous LTI system to be stable, this quantity should be less than infinity, and which is also we are calling as absolute integrable. That impulse response should be absolutely integrable. Next is invertibility. Invertibility, consider with impulse response HT, the system is invertible only if an inverse system exists, that when connected in series with the original system produces an output equal to the input of the first system. So this is, let us say, system which is impulse response HT, and here is this impulse response HIT. So if we are having an impulse response HIT which is somewhat like this, that the output of YT when as an input applied to this system, we are again getting the same output which is applied to the first subsystem. Okay. So if this type of system exists, then it is called invertible, and this second system called as the inverse system. Okay. So this is applicable for both continuous and discrete systems. Okay. So for this condition to be implement, if you will see this, if you will see XT convolution, HT convolution, HIT, this value will become XT. So this condition will only be hold when HT convolution, HIT should be delta T. Similarly, for discrete time system, this is HN convolution, HIN will be equal to delta N. Okay. So another problem is that if impulse response is like this, so we have to find out that whether the system is causal and or stable. Okay. So because you can see this system will start at n equals to -2 because of n plus 2. So this is non-causal. So this is non-causal, and if you will find out the stability, we will simply write this expression summation n equals to -infinity of Hn, and if you will write it, then because of un plus 2, limit will start from -2 to infinity, and when you will solve it, this value is 5, which is less than infinity. So that is why you can say the system is non-causal and stable also. And here are basically the references that I have used for preparing this presentation. Thank you so much.